Okay, so I guess we can resume. This is just a bit of advertisement. So there is this paper here, Supervector Machines with Applications, which appeared in Statistical Science recently. And there are a bunch of comments that are written by various people about this paper. And they, like, if you look there, you would find some discussion about these issues that I mentioned about, whether it makes sense or not to maximize the margin and these kind of things. So could be an interesting reference for you. Okay. Just give you five more seconds to write it down. Okay. And maybe I will just say a last thing about these things. So, I'm telling you, maximizing the margin is not necessarily the right thing to do. But still, the bounds are correct in the sense that the proofs are not wrong. So, but if you look at the form of the bound, then you probably would better understand. Typically, the margin bounds are of this form. You have the loss of your classifier is less than the empirical loss of this same classifier plus something that involves the norm of the classifier, which is the inverse margin times something, right? So what this tells you is that the smaller the margin, the closer the true and empirical error. But it does not tell you that when the margin is small, the error would be small, right? Which is what you would like to infer, but you can't. Yeah, sorry. So I always get confused. So the smaller the norm or the larger the margin, the closer the true and empirical. Which means that this can be arbitrarily bad. Like this can be a half, and this is a half or so. So indeed, they are close, but does not tell you that you get a good classifier or a good predictor. Right? The other kind of bounds that you can obtain are of the form, loss of your classifier is less than the loss of the best, say, regularized classifier, in the sense of the one that minimized true error plus norm of the function plus something. So this is slightly more interesting, and this something might also involve the the norm, but actually it would involve it might involve the norm. But the thing is, then you can say, okay, I'm doing almost as well as the best in my class, but then the question is still open whether this one is small or not. And this one is the one that minimizes, the true error plus, say, the norm. And it might be that this constraint forces you not to reach the right function. So the minimizer of this might be very far from the minimizer of just this. And in particular, this is the case. I mean, this can be arbitrarily far because of the no-freelance theorem. Because if these two were close, then these two would be close. And this would be close to this one, and that would contradict the no-freelance theorem. So you can always find cases where you can't really prove that the minimizer of the regularized risk or regularized error is close to the best classifier. Okay, and the only way you can make meaningful relationship is by introducing restrictions or assumptions on distribution. Okay, so there is no contradiction here. It's just that all these things are valid, but they don't tell you that this quantity would be small. They just tell you that this quantity can be related to some other quantity, which may be large. Yes?
What's the common assumption about the restrict probability?
Okay, so the question is, what are common assumptions for restricting the probability distribution? One typical one is to assume that there is no noise, which means that at each point you have perfect classification, and you can, in addition, but this would not really help. But in addition, you may assume that the target function, so this G star, right? So G star is the one that minimizes the loss. Typically, you would assume that G star belongs to some class. So maybe it belongs to your class. So this is typical, or maybe to some bigger class. And this would be, I mean, this is the standard type of restriction that you impose, that you have some kind of target function that belongs to a fixed class that you know in advance. And the distribution is derived from that, right? So which means the labels are, I mean, the labels are obtained by applying this function. But then, yeah, there often you don't have really restriction on how the x's are distributed, apart from, you know, they are in a bounded ball or something like that. Yes? Not sure to understand. So, yes. Oh, okay. The question is that the same, assuming that G star belongs to G prime, is that the same as assuming that, or as looking for G in a certain set of function? I mean, you have all sorts of results. So you have results that, like you are working with a class G, and you are looking for this Gn in this same class, and you say, well, what if my true function belongs to this class? Like, let's say these are linear classifiers. You say, well, assume that the best classifier is a linear classifier, and let's look for one such linear classifier and see how well we are doing there. Other cases is you look at G prime that contains G. So like you're trying to approximate, say, polynomials of degree 2 with with linear classifiers, say. Or, well, I mean, typically you would look for something where G is dense in G prime, for example. So G star would be picked from a slightly larger class, but then you hope that this class G can approximate arbitrarily well G prime. So there can be, you know, all cases, but it's, I don't know if that answers your question. Okay, good. So let's go back. So I mentioned these three ways of using the bounds. So either looking at the actual value of the bound, or using the value of the bound to choose between different models, or trying to look at really in a qualitative way at the bound. So the first case, the problem is that, you know, it's not easy to capture what happens with all these fluctuations, because we have a large class of functions. We already see that it's, you know, when we look at the binomial tails, it's not an easy formula to work with. And you imagine that, you know, all functions would have a slightly different behavior because they have different error, and they are all interrelated in the sense that, you know, if you look at two functions, the errors that they make are not independent, in the sense that, you know, the closer they are, the more similar the error that they will make. So which means it's all a mess, right? This empirical process is a very complicated beast. It's hard to really get something tight, or, you know, have an accurate estimate from calculation. So this is one reason for why the bounds usually have a large value, and, you know, you have large constants that are very hard to control and things like that. The techniques that we use, I mean, the only thing that we can say about them is that they are sharp in the asymptotic regime. So we can prove that, you know, the square root of n is the right rate asymptotically, but for finite values of n, we might have, you know, in the case of the chaining integral, which I told you is the right measure for capturing the deviation of the empirical process, you typically have some constant in front of the integral. And this constant might be very big, and also when you compute the covering numbers, computing the covering numbers is not an easy thing, and also in these covering numbers you might have very large constant, because you are always forced to kind of overestimate things. So, I mean, there are slightly more precise techniques than the ones I mentioned, but again, they are even more complicated to implement. So, in a way, if you want to have, and there is this trade-off, right? You can have bounds that are very large and very nice to write, like these kind of things, or you can have bounds that are a bit smaller, but that are completely unreadable because it would involve inverting the binomial tails and things that you cannot even write properly, or like that you cannot make explicit with a few parameters. So basically, if you want to use the value of the bound and you want to infer something from that value, because there are all these issues, you can't really, like, the value would be 10 or 100 or 1,000, whereas the error is between 0 and 1, right? So, I mean, it's better to use something like cross-validation or a test set if you really want to estimate the error that you're making. Now, you can say, well, okay, let's not care too much about the value of the error, but let's look at the behavior of that error. So let's say we have some parameter of our algorithm, lambda, and let's assume that we are, maybe the margin, or the inverse margin, the norm of the function, okay? And we look at how the bound behaves as a function of this margin. And bound meaning like these two terms here. So if I look at those two terms, maybe I compute them for some training sets and for all possible values of the norm, and I may get something like this. And this is like maybe from 50 to something. And if you look at the actual error of the algorithm, well, maybe it's something like this, and this is between 0 and 1, right? So of course we are off by a factor of 50, or sometimes even more, but still, we can think, oh, this is a good indication of where to look for the right model or the best model in a way. And what matters in this case is not how far they are, but really how far the minimum here is from the minimum here. And maybe they are not too far, so maybe it's okay to use the bound as a guidance to choose the right model. So what matters really is how the minimum is located. And in this case, there are many cases for which this kind of picture is what you obtain. I mean, in some cases it's completely off, but sometimes it does work. Especially for the margin, it kind of works. So there is some hope in this case. At least it's a bit better to use the relative value than to use the value directly. But again, I would not, bet that this is the best way to find the right value of your parameter. And sometimes cross-validation behaves better. It's more computationally expensive, so then it becomes a trade-off between how much computation you're willing to spend and how much accuracy you're willing to give away. Okay. Now, the third kind of use of this bound is the qualitative, and I think it's probably the most interesting one, where you look at the quantities that appear in your bound, and you're trying to infer from that ideas for building new algorithm. But you have to be careful, because as I told you, if the quantity that appears in the bound is the one that you have put yourself, like with these nested classes or with these weights, then it does not really help you, because you already had the intuition for writing the bounds. So I would prefer the other case where you do a careful analysis without any prior choice in a way, and you look at the complexity of your class, and you understand that somehow within the ball of the RKHS, it turns out that functions that are here, in this region of the ball, there is a denser set of functions than in this region of the ball, because when you compute your covers, you see something like this, and then you may use this information to tweak your algorithm in the sense that you want to look more in this region than in that other region. I don't have concrete examples, but that would be really the way to go. So this would not tell you what is the best way to tune on parameters, but it tells you how, how the complexity enters the game and how you can, what is the trade-off between the errors that you make and the complexity of the function class. But yeah, as I said, try to avoid to do it the other way, which is like start from the ID, get the bound, and say, oh, this bound justifies my ID. It's rather the opposite that you should do. So this is more reasonable. Maybe I'll skip that and go to this summary. So here are the kind of messages. Forget about the value of the bound is usually not very useful, but instead try to capture the meaningful behavior. And what I mean by meaningful behavior is that you should make sure that you're not confusing what you have put yourself in the bound and what is kind of coming out of the analysis. And what is important is to understand these deviations between true and empirical error. Where do they come from? Is it because you're just increasing the size by looking at bigger balls, or is it because there is some intrinsic property within those balls? And yeah, do not hope to justify your prior. Just get guidance. Let's see. Maybe I mean, this was a bit repetition of what I said before, so maybe I will. I mean, you will see the slides if you want to read them. I will skip to the kind of important messages, and then we'll try to save some time for questions and also to give you back the time that I've taken in the first few lectures. Okay, so if theory cannot help justify our priors, so what can we do? So this is the problem, right? The whole game of machine learning is you are given a problem that you have to solve, in the sense of you have to find a good classifier or a good predictor, a good model for that problem. And the whole idea is to find, I mean, okay, if you're a Bayesian, you have to encode your knowledge into a prior. And if you're not a Bayesian, it's a matter of trying to figure out how best to use the knowledge that you have. Because of course, if you don't know anything about the problem can be just anything, and no algorithm would perform well. So you can try your kind of favorite algorithm. You can try your SVM with Gaussian kernel, and that might work. But if it does work, the reason why it would work is because your problem magically has the right property of the target function being smooth with respect to the Euclidean distance, right? Because in the Gaussian kernel you have the Euclidean distance. So if it happens that, maybe I'll give this example again. If you happen to have a target function which is very smooth, then of course if you use a Gaussian kernel which is trying to, and you maximize the margin, which means minimize the norm in this RKHS, then of course if you have data sampled from that target function and you try to fit this data with a smooth function, you might get to the right function. But what if your target function is not smooth with respect to this Euclidean distance, but smooth with respect to just another distance that you don't know, right? Let's say your function is smooth with respect to the Hamming distance in the binary expansion of the x's, right? So you take x, you map it to this binary representation. Let's say you are between 0 and 1, and you take the decimal expansion in binary of your x's, and then you are looking at the Hamming distance between two x's, and that's your notion of similarity. And you have a target function which happens to be smooth with respect to this distance, which means like if you change just one bit in this expansion, let's say you change this bit, then the value of the function does not change much, right? So if this is the case, then you would have a target function which, looks like this, kind of a fractal kind of thing. So of course, if we use sample data from that, and you try to feed that with a smooth function, you don't then get the right thing, and you just perform bad, no matter how much data you get. in a way. I mean, eventually you might converge because the Gaussian kernel can approach arbitrary functions and so on, but might take some time. Whereas if you knew the right notion of smoothness, if you knew this, that you should be looking at the binary expansion, and you encode that into your prior or in your kernel, then you might immediately, with very few points, find the right thing. Okay? And how can you choose between those two? How can you, like, if someone comes to you with a problem, how can you tell whether this is, which kernel is the best? Well, you can't, apart from trying things and playing around or asking the expert about what he knows about the problem and this kind of thing. So that's why I'm saying it's more an art than a science. You can't really prove anything or justify anything. There is some, Bayesians would say if you are rational, you can do it, in the sense that rational meaning there is some kind of, maybe even a single way to go from what you know to deriving the right prior. And that's fine, but depends on what you know. So maybe another way to say that is, when you want to design an algorithm, you have two steps. The first one is to choose this preference or this notion of your prior or similarity measure or whatever. And there is no guidance. There is no proof, but you can get some guidance, maybe looking at bounds or things like that. But some people get their intuition from theory, some people get their intuition from practice, and it's just as fine. Theory is not the only way. And then you have to exploit this preference for inference, and that's where you can maybe formalize it a little bit more and prove results of the form, okay, within that choice that I made, because I choose the margin as my criterion, or because I choose this kernel or this something like this, I can prove that what I'm doing is not too far off from what I would do if I had seen the whole distribution. That's the only thing that you can say, and you can also see how these two things are different, like what you're doing on the empirical data and what you would do if you had full knowledge of the distribution, and get from there some intuition. And one thing which is important is also the computational cost. I will not enter into this, but that is really an important part of algorithm design. It's important, especially when you work on real-world problem and problems of large scale, to not only think about how accurate you can be, but also how much time it will take to be that accurate. And there is a trade-off there that you can also formalize. But so let's see. Yeah, this is, well, you can probably just read the slides when I will put them online, and there is nothing really. Maybe I just jump to the conclusion and then open the session for questions. Yeah, it's just some discussion about priors. So let's go to the messages, maybe. Okay, so now I will just, restate all the messages that I would really want you to keep in mind for the rest of your PhD/career. And of course, you're more than welcome to criticize or to comment or to react on these things. And I already mentioned that in the previous lectures, but I just want to restate them a bit. So, most important thing, we are trying to do induction here, not deduction. So we can't justify induction, which means the only thing we can do is use priors. They are needed, but we can't justify them. So this is really, really important. The only thing where we can get some control, like I was telling you these three forms of bounds: true versus empirical, and true error of your classifier versus the best classifier, and the last one was error of your classifier with respect to the best in a class. So the last one is what I call maximum regret, where you compare your performance to some reference class. And that's the only thing that you can control in a completely assumption-free or distribution-free setting. And you will see that again in Nicolo's lecture. shape of the bound that you should have in mind: 1 over square root of n. That's Hovding. If you have a finite class, you can just use the size as, the logarithm of the size as a complexity term. Then, if you use Bernstein or Bennett, like this refined bounds for the binomial tails, you can make the variance enter the bound and have the empirical error with this trick of inverting the bound enter here. So these are 3 kind of things that you should always have in mind somewhere. And the last thing is how does the geometric structure plays into this bound by replacing this term, this size, by something a bit more complicated, but that captures how how close the functions are in the space and so on. Maybe one thing I should mention is, and I should write, that typically if you are in dimension D, if your x's are in a subset of RD, like in a ball of RD, so let's say x is contained in RD and maybe even like in a ball of RD of size, say 1, whatever, doesn't matter, then the kind of bound you would obtain is square root of D over n. So the complexity, at least let's say for linear classifiers and for a large class of different classifiers that work in this space, typical behavior is of this form. If you, for those of you who know the Vatnik-Cherevodensky's dimension, I'm sorry I did not mention this in the lecture, but that was a bit intentional because I think it's not easy to relate this. It's a very, very nice combinatorial notion, but it's not easy to relate this to the metric structure of the class. And I think it's more important to understand that what matters is how the functions are related than to understand this special case in a way which is restricted to classification mainly. But okay, so for those of you who have heard about this, typical bounds that you would obtain with the VC dimension are also of this form, where D now is the VC dimension. So if you have a class of function which has VC dimension D, you would obtain things like that. And just a note, Vatnik's bounds are of this form. You have an extra log n factor here. And the chaining approach, which also works for VC classes, would get rid of this log n factor. And the other form that you may want to recall is when you have no noise, in the case where your target function belongs to the class, and you have 0 noise in the kind of ideal case, then all these bound, you can get rid of the square root, and you can get something like D over n, and here you can't get rid of the log n. So that's the optimal case or ideal case. So that's the best you can do in dimension D or VC dimension D, and that's in general. Okay, so these are things that it's good to have these kind of marks in mind. Okay. And using bounds, that's the last comment. It's important to understand that there are things that we that we might have put intentionally in the bounds, and there are things that come out from really the learning phenomenon. And these two things are, you should be trained, or you should train yourself to really detect which is which when you look at a bound. Okay, and finally, most important message is the goal. If you want to justify something, avoid assumptions, because as soon as it's fine to introduce assumption when you want to understand things, but you don't provide justification anymore. So if you put assumptions, you can't ever verify these assumptions. Like even the fact that sampling the instances is independent, this you can't even verify it. So anything beyond that is even less verifiable in a way. So if you avoid assumption, then you get justification. If you use assumption, you get understanding. You can say, oh, what happens if, let's assume if my target function were a linear classifier, what would I do? But doesn't mean that, maybe you have an algorithm that for which you can prove that if the target function is a linear classifier, you do perfect. But then what if it's not the case, right? Important thing, the geometry. And yeah, again, I'm repeating the same things again and again, hoping that it will, enter your brain and not get out of it. That's the last thing. And I'm sorry for this advertisement, but I had to do it. But maybe we can start with questions, and then I will come back to this afterwards. So, please. Yes. Okay, so the question is, I'm saying that the geometry is the most important thing in the bound, but the geometry of the function class depends on what you know or about on your prior. Okay, so what I'm saying here is, if you give me a class, of course you have chosen this class. So if you tell me I'm using, the RKHS corresponding to the Gaussian kernel, so I'm using SVM with Gaussian kernel, and that's my class of function. That's perfectly, that's your choice. But now what I'm saying is that given this function class, so okay, I have this function class, right, this RKHS, the geometry that I'm referring to is the geometry that is induced by the distribution when you look at the class. So two functions in this class would have some intrinsic metric distance between them, which depends on the probability distribution, which I don't know, sure, but I can, knowing this and maybe looking at, you can even look at an empirical sample and see how these functions behave, and then from that you can measure really, how big is the class and how the functions in the class relate. So this is no longer, this is, of course I would have to upper bound it, but this is something which is a property of the class still.
So the final term, like this chaining or the log n, or so, this is all an estimate of the geometry, but it could be a good one or a bad one, and you don't know if your method is the best. You can get totally different bounds, or different people can get different bounds for the same class because they have different knowledge how to estimate it.
Tell how. One thing that tells you that you are right is that if you look, for example, at the expected value of the supremum of the difference between the true and empirical, right? So this is more or less what these bounds are trying to bound or to estimate, how far these things are deviating over the class. So it happens that this quantity here, which depends on the class and depends on the distribution, you can prove that it's upper and lower bounded by, more or less the chaining integral with some constant C1 and C2 here. So what this means is that this chaining integral captures the right, at least the right rate of convergence of this to 0 as n goes to infinity. So this is a proof that this is accurate. Now it's true that it depends on how well you compute or upper bound these covering numbers, because then here, okay, this is log n, but you still have to compute this n, right? And you may have good or bad upper bounds on the n. But again, you can, in some cases, you can prove that, say, for example, for VC classes, you can prove that D is a good estimate, or, it's not exactly D, but say the covering number at size at radius epsilon is something like epsilon to the -1 over D, say, and this I mean, it's not an equality, it's an upper bound, but you can say that you can prove that it's an upper and lower bound, which means you have, within some constants, you have a good estimate of the covering numbers. So what I'm saying is that all these quantities, although it's hard to upper bound them precisely, you can prove that at each step you get the right rate, at least. You don't get the right value, but asymptotically they are correct.
So given infinite data, a Bayesian approach would also converge to the correct answer in some sense, because the prior is completely overwhelmed. And in many cases, they can also talk about how quickly the prior becomes overwhelmed. And it seems like you're doing this is a similar analysis. Can you contrast that point?
What you can prove in the Bayesian case is... Oh, repeat the question. Yeah, so the question is, in the Bayesian case, you can prove that after a while the prior is washed away. If you have enough data, then you can, you converge to the true thing no matter what your prior is, and you can even get results about how fast this happens and how does this relate to. Yes, yeah, sure. Yeah, I mean, this convergence, this consistency occurs only if the prior does put weight on all the functions, right? So it has to cover the entire rate. So yes, I mean, depends what kind of analysis you do in the Bayesian case. But what I'm saying is not. I mean, you can apply all these to Bayesian algorithms. That's all fine. You have your prior. You look at how fast this converges, and you can derive the same kind of results. You can have consistency, but you cannot have rates of convergence to the true, though, right? Because you have the North-Friedland theorem. So that's the North-Friedland theorem is also valid in the Bayesian case. It's just a matter of how you analyze things. Now, you have to make the distinction between Bayesian algorithms or algorithms that are based on using a probabilistic prior and using the Bayes rule to make to update the prior. So that's the Bayesian algorithm. But then there is the Bayesian analysis of algorithms, where instead of looking at worst case scenarios, you're looking at average case. So where every statement that you make in the Bayesian analysis would be on under the expectation over the prior, over sampling the functions according to the prior, right? So these are two different things. Bayesian algorithms can very well be analyzed in that framework, or SVMs can very well be analyzed under expectation over some prior, right? So, and the kind of result that you obtain with Bayesian analysis are kind of similar, but they tell you something different because you can't really. I mean, they tell you something on average over some prior sampling. Doesn't really tell you something about the problem that you're looking at, right? Because it's just average over a set of problems, and you only get to see just one problem. So, does it mean that you can derive something from this average? I don't know. It's a matter of choice, but again, it can give you some guidance, but it does not justify really something for your specific problem. Just like these bounds, they are probabilistic in nature, so they tell you something about the distribution over all possible training set that you would sample. But for this particular training set that you observe, maybe it's true, maybe it's not true. Maybe you are exactly in the case where the bound is violated, right? But you can circumvent that still by looking at this transactive setting that I mentioned before, or the online setting where you don't even have this issue of probabilistic bounds and you have deterministic bounds. Yes?
In practice, we cannot get rid of prior, and we always use prior assumptions in dealing with practical problems. And I always wonder how much I gain from the prior assumption and how much I gain from the data. And is this a valid question I can be considering with learning theory? Okay, so
this question is perfectly valid, right? You have your prior assumptions and you have your data, and of course, if you have more data, this kind of replaces the amount of assumptions you need or amount of prior knowledge that you need. So either you know a lot about the problem, and then with few data you would identify quickly the right predictor, or you don't know much, and then you need a bit more data to first refine your prior maybe, and then do inference. And the question is whether the theory can help here. I would say you can probably quantify. I mean, I have not seen result of this exact form, but I would say you can quantify, within a certain prior, how well your algorithm is doing, and then, by looking at the data, what you can do is typically measure something like this, measure the empirical error on this data, and that would give you an idea of whether your prior matches with the data, say. And I mean, there are results, for example, that are based on making things in 2 steps. Like you have your training data, you use the first half of your training data to adjust the prior, let's say, or to adjust the parameter of your algorithm, and then the second half to learn. And you can prove that you would converge to the right choice of the parameter with the first half of the data, and then with the second half you would choose the right function in that class, for example. Like if you use the first half of the data to choose which ball in your KHS, for example, and the second half to choose which function in that ball, you can have result that shows convergence or things like that. So I mean, it's maybe not really a direct help, but it goes in that direction.
Maybe a follow-up question on this one. So the last question was about the influence of the prior on your inference. But is there also something to be said about the influence of the model that you've chosen? Say, maybe your model is not exactly correct, but good, say in a non-parametric setting. So is there could learning theory say something about the robustness of your procedure to slight errors, say, in your model?
Can we... yes, you can quantify. I mean, like, there are results of 2 kinds when you restrict yourself to... I mean, you can say, well, what if my target function is a linear classifier, let's say? And you can get results that say, well, if the target function is a linear classifier and you're doing empirical risk minimization over linear classifier, then you get this much error, say. And then you can say, well, what if my target function is differing from a linear classifier by a certain amount? How much would I lose in the bound? And then you can quantify. So you can say, well, if the distance between the target and the class that I'm using is this much, then I would pay this extra price in the bound, let's say. So you can indeed relate, but you need some kind of notion of how close your target function is from being in a perfect class or something like that. And then you can get results, yeah. Yes.
Okay. The results in learning theory, basically they capture like the average behavior, right? So you're computing the risk, which is like the average loss. So in the first lecture you talked something about the Minimax rules. So are there studies on Minimax in learning theory setting? Because you're trying to find a rule which does best over like a class of distributions, and here we make an assumption saying the distribution is fixed. Assume that the distribution actually changes over a set. Probably doing Minimax is better. So
Okay, so I mean, I'm not sure to understand what you mean by the distribution is changing, right? I mean, usually you have one problem, and this problem corresponds to one distribution. And here we have not, I mean, the results that we obtain are not on average. They are probabilistic, which means that they hold for, a certain percentage of the training set that you might observe. But they are kind of worst case in the sense that we're trying to say for this, I mean, it can be that for certain training set it doesn't work, but for most training sets it will work, which is different than from saying on average over all training sets we get this much. I mean, the kind of result that we would obtain would have a similar shape anyway. But the question of whether you should look at the given, the Minimax results really are the same. They are looking at the worst case over a class of possible distribution. Here we have looked at the worst case over all possible distributions because we have said, okay, the distribution is fixed, but we don't know anything about it. So basically the bounds are valid for any possible distribution, which means including for the worst possible distribution. Minimax results tend to look at restricted sets of distribution, which is fine, which is what I mean, at some point I mentioned that like if you look at results comparing your classifier to the absolute best, you can restrict your set of distributions and get results in the sense of that tells you how fast you converge, provided that the distribution is within that set, and even if it's the worst in that set. And these are useful. Like, for example, you may assume, okay, let's say my data lies on some low-dimensional manifold, right? I can't verify this, but I want to know whether I can exploit that with my algorithm. And using this restriction and using a certain algorithm, you may prove that your algorithm is actually able to exploit that restriction in a meaningful sense. And this would tell you that your algorithm does well if the data is on this manifold. Now, if it is not in such a manifold, your algorithm may not do as well, but that only practice can tell you. But it's a good way to design algorithm. You say, well, let's assume this restriction. Let's consider that it makes sense in practice. Let's get the algorithm, prove that it works in this restricted context, and then let's try it on actual data, and maybe it works if this is fine. I mean, this restriction that we put is actually verified by the data. It's a natural way to derive algorithm. But,
is there a theory on unsupervised learning?
Yeah, is there a theory of unsupervised learning? There are theoretical results, but yeah, of course, it's much harder to define what is the goal, right? You don't have a notion of error if you don't introduce some criterion. So typically, the kind of result you can obtain is assume you have some criterion, like in the k-means clustering, you look at the say the ratio of intercluster distances with intracluster versus intercluster distances, something like this. And what you can say using this kind of approach is you can say, well, I'm minimizing this criterion on my data, but does this converge to the best or to the minimizer of this same criterion on the whole distribution? So the kind of result that you can look for are results that relate the empirical thing that you're doing to the true thing that you would do if you knew the entire distribution. These kind of results. But it's much harder because there is no agreed upon notion of what is a good clustering, for example. So you have to first choose your notion and then prove that your algorithm is not too bad with respect to that notion. Okay, so let me come back to my final slide just to say that at Google we are hiring many people, and for two kinds of positions. Oh, sorry. Yeah, so you can see. We offer lots of internships, so feel free to apply if you're interested, and especially like PhD students, it's a good way to get a feeling for what Google is doing or for what industry is like, and also to apply what you have learned in a more practical setting and work on really large-scale, exciting problems. The duration, it can be like, the minimum is more or less 3 months, and it can be 6 months or even 9 months. And it's also a great way to be hired at Google later on. There is a very high conversion rate from interns to full-time. And the positions are offered all over the world. For full-time, I mean, there are positions all over the world also for full-time. But if you are from Europe, it's easier to get a position at Zurich because you don't need a visa, or I mean, you don't need the same kind of visa than for the US. And there are many software engineer positions there. And if you want to know more, just go to the website or send me an email. Okay, thank you very much.